Hi everyone, my name is Christian and I'll be going over today's tutorial on optimizing the core of a curved composite panel. Now I'm carrying on from the previous tutorial. I basically did not skip a beat. In the last tutorial we basically perform a topometry optimization. Basically we wanted to identify where in the core do we need really thick sections and where in the core do we need thin sections. So here you can already see from the topometry results that I need a thick core here, and I need a thick core here also. So let's go ahead and start talking about the goal for this workshop. So we're going to take that data that we created with topometry optimization, and we're going to feed it into, or we're going to input it to the Vero web app. We're going to use the Vero web app to construct core shapes, if you will. Let's see. So right now, we don't know what the new values are going to be once we optimize the thickness of the core. But what we should see is we should see a reduction of the original mass. So you'll see that in a few moments. Also, we want to make sure that the buckling load factor is greater than 1.0. So those are some of the goals. The loading is going to stay the same as it was before in the previous workshop. Here is an overview of the different core sections we're going to build. We're going to build a core section here in the top, a core section here in the bottom, and then a core section here in the middle. And just so we make sure that we have a core everywhere in the panel, we're going to build another core piece for this other region. So that's going to constitute our core. So let's go ahead and see if there's anything else. Right, let me discuss what the optimization problem statement is for this workshop. So as always, please take a few moments to draft out what your variables, your objective, and your constraints are. This will help you when you need to talk to somebody else about your optimization problem, or when you're configuring your optimization. It always helps to have the problem statement written out. So we're going to create a separate core for PCOM G2, PCOM G3, PCOM G4, and PCOM G5. For each of these different cores, we're going to specify a ply thickness variable that you see here on the left side of the screen. We're going to minimize the weight while making sure the buckling load factor is always greater than 1. Now, the appendix is going to go in greater detail regarding this workshop. I recommend that you refer to that appendix for more information. So let me go ahead and make sure I at least go over the appendix very briefly. So I'm going to scroll to the very bottom. Right. So here's the appendix. I recommend that you go through the appendix maybe before this workshop or after this workshop, just so you get an idea of some of the other information that's useful for this particular workshop. So I'll go ahead and flip through here, and then we'll go ahead and go back to the beginning of the workshop. And now where are we at? Right. Okay. So as always, you're more than welcome to contact me if you have any optimization or machine learning related questions for FEA or CFD. If you want access to any of the tools that I show you today, you're also more than welcome to contact me here at this email address. Now let's go ahead and get started. And let me make sure here on my other window I have the necessary notes. Okay, so let's go ahead and get started. Now, I'm going to continue on from the previous tutorial, so you can see that I already have a lot of those files. If you want to start fresh, this is what you would do. You would go to the user's guide, go to the composite tutorial section, scroll until you find the tutorials for the curved composite panel, and then here click on this file link, and this will download all the starting files for today's tutorial. So I already have those tutorial files because I'm continuing on from the previous workshop. Let me go ahead and do this. Let me open up the viewer web app. So let's go ahead and go to the full list of web apps and open the viewer web app. And the first thing we're going to do is we're going to upload the bulk data files with the topometry entries. So remember, the viewer web app accepts the following files. The viewer web app accepts the BDF files with the tomvar entries, and it accepts the .ply files. So let's go ahead and upload those files right now. So here we'll click on select files. We'll go to the directory with the successful topometry optimization. We'll click on upload results. And then we'll click on topometry here in the far right hand corner. We'll click on select files and we'll navigate to the same directory. And here we'll select the ply 0005 file. And now we'll go to ply shapes. We'll minimize this window and then we'll create three ply shapes. We'll click on front here and we'll move this to the side a little. Let's go ahead and move this to the 50% mark. Let me actually go back and maybe go back to 25%. Right, perfect. Okay, so this is what we're going to do. We're going to use this option. We're going to use the results from the topometry optimization to construct our ply shapes. So here, let me click on the edit button. This is going to let me spread the ply shape. So here I'm following the results of the topometry optimization. And now if I accidentally spread the ply too far, that's okay. I can just go ahead and remove the plies by clicking on the remove button here. If you want to remove or add a ply, you click and hold the left mouse button and you move the sphere to either add, spread, or remove the ply. So this is the first core thickness that we're going to have. Let's go ahead and repeat the process for this other section. So we'll go ahead and do this. Now, I'm going to diverge a little from the workshop. I think in the workshop, I had these ply shapes, or core shapes, core shape 1, core shape 2, and core shape 3. So let's see, should I diverge or not diverge? Maybe I won't diverge. I'll just stay with this. So here, let's go ahead and do this. We'll go ahead and spread the ply. You'll notice one thing with the data from topometry optimization. You get proposed ply shapes or core shapes that cannot be manufactured. So what I'm doing now is I am deciding where the core is going to exist and where the core is not going to exist. That's what I'm doing right now. And then here, for this last one, let's go ahead and remove the core from here. And from the bottom too, we'll go ahead and remove the core that you see here. And let's see. Let me go ahead and spread this. Now, there's one thing to be careful about. Let's click on View PCOM-G zones. You don't want to overlap the core multiple times. If you look here, you'll see that for PCOM-G2, there are 2 core layers. So right now, if you look here in this table, you'll see that the checkbox is marked. This core layer, if we display it, is a continuous core that spans the entire panel. The second core shape is also overlapping the other core layer. So that's why if you look at the PCOM-G zones, you see this 0 core 2. And for this other PCOMG, you see 0 core 3. That means that there are 3 core layers that are overlapping. But we only want 1 core layer for each of these PCOMG entries. So what do? Click on Options. Here in the Core section, click on Enable checkboxes including PCOMGs. When you click on this button, you now can control a majority of the layers. So if now we turn off the core layer that's fully continuous, let's go ahead and turn it off. And if we look at the PCOMG zones, before it said that there were 2 core layers overlapping, but that 2 is no longer there. There's only 1 core layer there. Before, for PCOMG 5, there were 3 core layers that were overlapping, but now it's reading that there are 2 core layers. So let's go ahead and now continue on here. How do we fix the second core layer? So here you see that there's some overlap here in this beige region. If you can see that. So here, let's go ahead and maybe position this. You'll see that this line here is going to line up with this line of the interface. We're going to use that as a marker. So if we look here, one of our layers is overlapping, right? So here, this core layer is overlapping with this core layer. So we need to fix that. And here what I'm going to do is I'm just going to use my finger, surprisingly enough. And I'm going to use the remove button. And I'm going to remove the core from that particular region. So now if we look at the PCOMG zones, before it was reading that there were 2 core layers that were overlapping, and now there's just 1 core layer that's overlapping. But you have to be careful because for the other zones, you have to make sure that there's only 1 core layer overlapping. So here, I still need to remove the core from here. And you'll see this updated in a moment. Previously, there were 2 core layers, and now there's just 1 core layer there. Let me go ahead and clean this up a little bit more. Maybe I say that, okay, I can't manufacture this. This is too difficult to manufacture. What you can do is just remove the core and spread the core as you see me do here on the screen. And now let's go ahead and look at the PCOMG zones. Now there's one problem. This green PCOMG does not have a core layer. Now this is a problem for us. Now what you could do, you could just create a new core layer and you can just start filling in where you think the core does not exist. So for example, I know the core does not exist here. I know the core does not exist in the bottom too. But this could be a little tedious. So there's an alternative to do this. You can click on Add Complement Core. And first, let me go ahead and delete this current layer. The Add Complement Core option is going to take the, I don't know if inverse is the right word, but I think in mathematical terms, the term is called intersection. Let me go ahead. Math intersection. So in formal math, there's this concept of intersection, or maybe it's not intersection. I forget what the word is, but basically, I think it's called a complement, actually. Let's go ahead and look up complement. And I hope I have the spelling right here. Okay, perfect. So basically, the complement is everything outside of the current selection. So here, if this core layer is here, this core layer is here, and this core layer is here, when I take the complement, it's going to pick everything else but those other core layers I just showed you a moment ago. So that's what this button does. It creates this complement core. If I go back to view PCOMG zones, I now see that I now have 1 core, 2 cores, 3 cores, and 4 cores. Each PCOMG entry has its own core layer, if you will. Now, let me look at my notes very quickly and see if there's anything else I should be doing here. I don't think I there's anything else to do. Right, okay. Here, let me just show you what I'm doing. I think I'll do it here on the screen. I'm basically just going through all these different slides just to make sure I'm not forgetting a step in my procedure. Here, I think you saw me go and make these different core shapes, if you will, based on the results of the topometry optimization. And here, let's see. Apparently, there is one adjustment I need to make to the core thickness. So let's go ahead and jump out of here. Now, this section is traditionally reserved for a ply number optimization, but here I'm going to still specify a so-called ply thickness. The reason I'm doing this, I want the web app to generate the thickness variables for the core thickness. So that's why I'm purposely building. This is why I'm purposely supplying these dummy ply thicknesses. You'll see why I'm doing this in a few moments. And let's see if there's anything else here in the workshop. Okay, use ones. And now we are actually going to use the offset in this example. So here, let's go ahead and use above. Now, when you use above, that's going to set field 3 to 0. So here you see all the offsets are equal to 0. And that's basically what we want. We want the composite to be offset. So I don't think this is done right now. No, right now the composite has no offset. So half the thickness is below the mold line, if you will. The other half is above the mold line. When we use this option here to offset, basically what we're saying is that we want the composite to be shifted above the mold line, which is represented by the 2D elements that you see here. So now that we have that, let's continue on with this workshop. Now, I should mention which workshop mentioned this in greater detail. If you want more information about that offset, I would refer you to the first workshop, I believe, in this whole series. Right, the first workshop in the series, maybe it was the second series, talks more in detail about this, and I think I'm looking at the wrong workshop. So this is going to be the phase B workshop, and I think it might be worth closing one of these workshops. So here, so if you refer to phase B, there is this long discussion about the offset and the normal of the elements. I refer you to this section so you can read more about the offset that we're using here today. And here we're using the above option. Let's go ahead and carry on. So 1, 2, and 3. And I think we're ready to go. Let's go ahead and save all these bulk data entries. And here are all the new entries that are going to be added and updated in the bulk data file. So let's just go ahead and download the new set of bulk data files. And we'll call this new zip file 5 core shape output. And we'll extract the contents of this file. So if you remember before, all of these 2D elements were using only one pcomp entry, which I believe, right. So maybe this is not the right file to use. If you look at the very starting file, all of these C quad 4 entries were using the same PID of 1, which was corresponding to pcomp 1. Now, after we went through this procedure of breaking up the core into these individual sections, we now have multiple pcomp G entries, and all of the 2D elements have been updated to use different pcomp G IDs. So you see some of these are pointing to pcomp G 2, 3, 4, 5, and so on and so on. Okay, so now what's next? We still need to finish configuring the variables for this core thickness optimization. So let's go ahead and open up the optimization web app. And we'll go ahead and upload those files we just created. And I think it might help to close some of these windows right now. And then maybe I'll close some of these other Patreon windows right now also, just to clean up the desktop a little. And then let me keep closing all of these windows. I noticed that the desktop has become very cluttered. Okay, so let's go ahead and open that set of bulk data files. We'll go ahead and upload it. Now, for the objective, it's still the same weight objective. The constraints should remain the same. The subcases, everything is left as is. We're still doing a statics and then a buckling subcase, and then we're still assigning the load factor constraint on subcase 2. Now the variables. We need to modify the variables a little, because right now they're in terms of ply thickness, which is something we don't want. So if I look at the tutorial, let's look at the adjustment I make. Okay, we're going to make this adjustment. So let me go ahead and move this to the other window. Right. Okay. So let's go ahead and navigate to the variable section, size. And the first thing we want to do is, if we click on options, we have the option to turn on the label comments. This basically lets you customize the description of the variable. Now this is useful if you have maybe 1,000 variables. You'll want to differentiate each of these variables. So here I'm going to do that right now. Thickness of core layer. And let me go ahead and delete some of this. And now what I can do is I can just copy this description to the other ones. Okay, now we need to make one adjustment here. These Y1 variables are going to be what the description says, the thickness of the core layer. Now, we want the thickness to range between 3 and 25 millimeters. And remember, we're dealing with half the thickness. So here we're saying that the core in total should range between 6 millimeters and 50 millimeters. So let me go ahead and copy this to the other ones. And now you see I'm getting some error messages. These errors are because the initial value of the variable is outside the lower and the upper bound. Anytime you see a red status icon, that means you'll get a user fatal message during the optimization. So here we'll go ahead and fix this. We'll say that the initial core thickness, if you will, I believe 5, right? And if you remember where we got the 5 from, in the very first tutorial, we performed a constant thickness optimization. It is from this baseline thickness optimization where we got the value of 5. So if we look at the results, this is where we got the value of 5. So we're just going to try and start from the same starting point. So 5, 5, 5. Now this is going to range between 3.0 through 25 in the increments of 1.0. And let me make sure that the workshop, or rather I'm following the workshop. So let's go ahead and copy that here and here. And let me minimize this. And let's see if there's anything else I need to do. Right, okay, everything looks like it's the same. Let's make sure that we're still using the truss region. So here, when it comes to simple size optimization, typically I like to use 20 design cycles. Let's see if there's anything here. Let's turn on the trust region, so that's on. And now let's go ahead and download all these updated bulk data files. And then we'll rename this file ply, or not ply, but 6 core thickness optimization, maybe sections, and then extract all, and then we will go ahead and start this. So right now we're using Nastran Sol 200 to determine what the core thicknesses should be for each of these different sections in the model. If you recall, we have, I believe, 4 different zones. And so we want to determine what should the thickness be of the core for each of these individual sections. So that's what's happening right now. We'll go ahead and sit back for a few moments and let this finish. And now that the optimization is finished, we'll go ahead and look at the results. Now, remember that the mass, when the thickness was 5, gave me a total mass of about 4. And now let's look at what the new mass is. And here, let me look at this workshop D. Let me go to that table. So here we had a starting mass of 4. And if we look back at here, we should get a mass of 4. At the very end, we get a mass of 3.43, and I believe that's what's documented here. So here we get a slightly, or no, that would be this column here. So here, let me maybe make it underlined. So this is the mass we get. Here, when I repeated this workshop, I got 3.44, but today I'm getting 3.43. If we were to take the difference, subtract the mass of the plies from the total mass, I get that the mass of the core is 1.7. And actually, I should double check that. So let's go ahead and open Excel real quick. And I'll go ahead and copy these 2 values there. So that's the mass. Let's look at what's happened with the constraints. The constraints are originally negative. So that means that we satisfy the constraints. Anything less than 0 means you're satisfying the constraints. Anytime you're above 0, you're positive, you're violating your constraints. And then towards the end, we have a value of negative 0.004. That means that we're satisfying the constraints by 0.4%. And here in this next table, let's go ahead and look at some of the thicknesses for the cores. So here, all the core sections started with a core thickness of 5 millimeters. Now, each section has ended off with their own value of core thickness. So here, let me do this. Let me take these mass values and let me make sure that I'm doing the arithmetic here properly. Right, so I do get 1.7 as a mass. And now what's the buckling load factor? You can either use Patran to look at the buckling load factor, or you can look inside the F06 file, and there are a few places where you can get the buckling load factor. You can either get it here in this responses table. So here we get a buckling load factor of 1.0041. Alternatively, if you look at this section called the real eigenvalues table, you'll see that we get the same eigenvalue value there. Now, typically when you're done with your optimization, your updated entries are outputted here in the punch file, the .pch file. Then you have to copy these entries. Then you have to go back to the original file. And then you have to go ahead and copy and paste that here and go through this elaborate process of manually updating your entries. The alternative is to look in the workspace B file. In this file, the thicknesses for the core have been automatically updated for you. So here, the core thickness in this section is 3. The core thickness here is 7, 3, and 4. Now you might be wondering, okay, what does this look like visually? We'll go ahead and open the viewer again. And we'll go ahead and upload the file that's found in that workspace B directory. And we'll open the model display panel, we'll maybe change the color of the background. We'll look at the left side of this model, and maybe we'll look at the G-plies. Now the G-plies are going to show you a tapered look at your curved composite panel. So here, if I look at this section, you'll see that my pliers are being tapered. Now, this core thickness, it's either going to be 7, right? So remember, this core thickness here is 7 millimeters, but the total core thickness is 14 millimeters. This next core thickness looks like it's about, let's see, I want to say maybe 3 millimeters. This might be 3 millimeters. And let me zoom out actually, just to make sure. So maybe I have it a little backwards. So this part of the core is 7 millimeters. So this core is 7 millimeters. This next core is 3 millimeters. And then this other part is 4 millimeters. So that's here. And then here, let's look at the right part of the model. So if you remember, we configured a core thickness, a different core section, if you will, here. This beige looking part of the model. This is where PCOM G5 is. What does the thickness of the core look like there? You'll see that the core actually, let me just hide all of these. And let me just display the core thicknesses. And let me hide the model display panel. We'll give it a few moments for the thicknesses to regenerate. And here's the final result. So you see that the core took on unique values of 7 and 4 in these two sections. So here, the core thickness is 7. The core thickness is 4 here. And then for the middle, the core thickness is 3 millimeters, a total of 6 millimeters. Here for this other section, the optimizer has determined that you really don't need a very thick core here. So it's actually reduced the thickness to 3 or a total of 6 millimeters. And one last comment here. If you recall, in the Viewer web app, when we were configuring these different cores, we used the offset above relationship. And here we can see the impact of that offset here. In this line that you see here, this represents the 2D element surface. This represents the outer mold line for this example. We have actually gone ahead and used the above offset. So the entire composite is now offset above that 2D nodal surface. And then here, just one additional last comment. Right now we're looking at the G-plies, and when we look at the G-plies, they are going to be tapered. So you see here the plies from the top of this core are tapering into the plies of this core. Maybe you don't want that, so let's go ahead and turn that off. Let's go ahead and only display the PCOM G plies. And let's recolor it. So here you see a more PCOM-G-like look at the layers. So I just wanted to mention this because you might prefer to look at the tapered G plies, or you might want to look at the plies as defined by the PCOM-G entries. Now let's go ahead and see if there's anything else to add to this workshop. I'm almost approaching the end of this whole workshop series. Right, so one last thing. The file in workshop or workspace B, this typically has the case control command. But if your optimization involved a multidisciplinary optimization like was done here, remember one subcase was statics, the next subcase was buckling, the final bulk data file will not have the case control section. So what you can do, you can just go ahead and copy the old case control section. So let's go ahead and open that file. Let's go ahead and copy everything above the bulk data section. Let's copy it to the final bulk data section. And let's go ahead and paste it. And let's go ahead and save it. If you want to, you can remove the old bulk data entries for the optimization. So maybe let's go ahead and do that right now. So let's go ahead and highlight all of these old entries. Let's go ahead and delete it and save it. And now what you can do, you can go ahead and run Nastran. And that bulk data file is going to be a buckling bulk data file. It's not going to be Sol 200 anymore. So let's go ahead and open the F06 file. And then here, if we look at the eigenvalue, you'll see that the eigenvalue of the buckling load factor is 1.004, which is greater than 1.0. So now you can take this bulk data file, you can send it to another colleague or do additional work. And we're pretty much at the end of this tutorial. I'll say this. Actually, let me make one last comment. And I don't know if I have that information here. Let me go ahead and open another tutorial file. So for those who have been following my tutorials so far, you'll notice that in this tutorial, I actually performed a topometry optimization. In the other tutorial, where I was considering failure index constraints, I did not consider a topometry optimization. And this is why. If you're dealing with ply stress, ply strain, or failure index responses, when you perform your topometry optimization, you're going to get a solution that just does not make any sense. And the fact is that when it comes to composites, there are thousands of local optimization solutions. This is why you're going to get these really odd results that you cannot interpret. Even though it's one of many solutions, it's unusable for us. Again, if you look at these results, you're going to ask yourself, okay, how do I build my ply shape? Should it look like this, or should it look spotty? What exactly is going here? So when you're dealing with element responses like ply stress, ply strain, failure index, or strength ratio, as I mentioned in the other tutorial, I recommend building your ply shapes that follow the contours of your failure index responses. That's what I recommend. If you're dealing with non-element responses, for example, you're dealing with maybe buckling load factors as we did right now. If you're dealing with natural frequencies or displacements, I have seen that topometry optimization will give you good results. If I go back to, I think it was C, no, the wrong C. If we look at the other workshop for this curved composite panel, you'll see that the topometry results were actually reasonable. Here, we got results that we can interpret properly. We know the core thickness should be greater here and here. But if you're dealing with element quantities, it's not so clear sometimes. So that's why my recommendation is, if you're dealing with displacements, natural frequencies, buckling factors, anything that's non-element, consider using a topometry optimization to get a suggestion as to where to put your plies or your core. If you're dealing with these element quantities, I recommend manually building those .ply files and following the contours of the French plot to build your ply shapes. So, just as a last comment, now what happens if you want to consider both element quantities and non-element quantities? Suppose you want to consider both of these. You'll have to use a so-called hybrid method. You'll have to combine both of these methods together to suggest your ply shapes to build. So that was the last thing I wanted to mention in this whole workshop series. I hope you found this workshop very useful. If you have any comments, if you have any feedback, recommendations for the next tutorial, you're always more than welcome to contact me. If you want to use the web app that you saw today, also you're more than welcome to contact me here at this email address. With that, thank you so much for watching today.